Thank you. Thanks to the organizers for this very lovely workshop and to all of you to stay until now. Well, yes, today I'd like to have a conversation about what I understand so far about the memory of Seedbank effect and talk about what we can do in practical terms where the word practical has to be taken with a grain of salt. So one of the reasons why we are here and why we sort of are kind of encouraged to keep investigating the Seedbank dynamic in population genetics is because of this paper of York and is there anything? I think they can hear me. I don't know. I hear myself with some sort of echo, but it may be some.
Yeah, here.
Ah, I see. Good point. And now what should we do? Well, I moved this. That's it, no?
Yeah. Say something?
Yeah? Good. All right. Forgive me. I meant to say that this is the main model that has boosted sort of the optimism in terms of ability to make dormancy tractable mathematically. And of course, this is the diagram that we are all become accustomed to, especially in this week. And that's the diagram that has allowed mathematicians, Jochen, Adrian, Maite, and so on, who produced this model to be able to talk to biologists and be convinced that this is a sensible model to look at, after all, for Seedbank, and to model Seedbank effects where maybe the stretch coalescence was not a good interpretation of the corresponding genealogy. By the way, today I'm very happy to have to be in a day where there will be a lot of very nice pictures that we saw. Previous talk was very nice. This is as good as it gets in my talk, right? So don't expect anything better than this. And yeah, so what happens here, we have two islands, say, one is the dormant reservoir, one is the active reservoir. We have a rate to wake up and a rate to fall back into dormancy. And you keep spontaneously and randomly switching between the two states. And what this model has generated is an explicit description of the allele frequency random evolution forward in time in a right Fishery way that has a very nice connection for comparison with the multi-island model that is well understood both in biology and in mathematics. And that's another big point. And another thing is an explicit representation for the genealogy, extension of the coalescent stochastic process. And the duality has been formally established between the two. Everything makes sense dramatically well. And one of the features of this model is still that although you manage to overcome the assumption of bounded Seedbank effect, the so-called weak Seedbank effect, it still limit the memory of the process in a way that can be summarized as the wake-up waiting times are exponentially distributed. And that's actually acceptable in many cases, I suppose. And so overall, it's also very well understandable why is that the case? Because, of course, when you are in a dormant, let's think in discrete generations. If you are in a dormant state, you always flip a coin with a probability of success that is proportional to E, the parameter of switching back. And if you succeed, you wake up. If you don't, you try again next generation, right? So this is a coin flipping experiment. The coins are IID, so the probability of waking up becomes geometric. The geometric distribution is a memoryless property, as a memoryless property, which is what in the continuous domain becomes exponential, right? The exponential waiting time is very nice because it's responsible for the Markov dynamic in the extended two-island setting, at least. And is light-tailed, right? So we know what the exponential probability density function looks like. But does it have to be like that in reality? I mean, that's a convenient aspect of the model, but is this always a good model for real life? And I think that we have had plenty of statements, even in this workshop, that encourage us to think that maybe we could go beyond the assumption of light-tailed memory. And I got, let me see what I put in the slide. So there is this excerpt from the recent paper by Lennon and a subset of this audience, and where it says that at any given point in time, an individual sample from the seed bank may rest in a shallow or deep state of dormancy. Well, shallow and deep may have a lot of meanings, and I know that there is a diversity of organisms. So the memory of the waking up time, let's say, the memory of the seed bank may be heavily affected by how deep you are in your seed bank, right? So there are marine sediments that actually are physically going deeper, and for them seems to be harder to wake up, right? And there is this famous already seen quoted in this workshop paper by Morono and Al, where the title is quite astounding because say that dormancy will persist for a number of years that is in the scale of 101.5 million. That I imagine waking up then and see what the world look like. Yeah, and so that means that maybe light tail is not always a good assumption. And also, if you remember Nathan's talk yesterday, there was also a discussion as to whether long-lasting dormancy, longer than order of n generations, for example, would make sense. Okay, so there is no prevention. Let's say there is no logical reason for not looking into fat tail distributions for waking up time. Okay, so, and that's possibly the message I'd like to convey with this talk. I could close it here, but then I have a few considerations that I want to make and share with you about what I understand so far about dormancy in existing models of population genetics, and also try to explore and show you the initial step for an exploration I'm involved in how to perhaps make them amenable for inference in some way. Okay, so this is mostly work in progress, and it's been work in progress since 2015 because the memory was in our mind already when we started looking into seed bank models back then. And you know, we are continuously thinking, but not always active. So sometimes, at least I'm personally not thinking continuously about memory because, yeah, anyway, we have lives. Okay, and part of the people involved in this talk are also from Warwick. Especially the statistical part, I will explain is a recent work with Massi Tamburini in Warwick, but other people may be involved later on. Okay. For example, Yaro here and Marta here. Who knows? Okay, so this is a seed bank with seed bank diagram that you have seen in Karlskron and Lascaux, and the thing is that this graph is really a good representation of potentially any general seed bank dynamic, right? So that's what we had in mind as a general model for seed banks in before 2016, right? Before the seed bank coalescent came about, right? So you just had a bounded number of generations in Karlskron and Lascaux that you could skip. And the main thing we did is to make them potentially unbounded. Okay. And the generation of the parent is chosen according to some generic probability distribution mu. Essentially every individual has the same distribution mu to choose the generation from which they select their ancestor and their parent actually. And within that generation, they sample parent uniformly at random and inherit according to your favorite inheritance mechanisms. You can add mutation, you can add selection and so on. But for the moment, I'm just assuming nothing but you inherit the type of your parent. Okay, and then this sort of ancestral throwing of edges between generations defined a graph, and any two individuals in a given generation that end up selecting the same generation and the same parent are siblings. And that's how you reconstruct the genealogy. The point is that when mu is bounded, of course, we know that the result of in the genealogy is the stretch coalescent, and it's I haven't read it around, but perhaps there is also somewhere written down. I expect a Wright-Fisher dual process is possible to write. Oh, you did it. Okay, very good. Sorry. And yes, and that's all very sensible. For mu with unbounded support, there are different qualitative regimes that you can obtain according to the tail of mu. And this is a list of the results that we could obtain back then, right? So if the tail of mu scales as a power alpha, say, of n's, and times a slowly varying function, the parameter alpha separates the class of possible mu's in three regimes. One is when alpha is less than 1 half. In this case, any two lineages may not ever coalesce. So in this case, we don't have a single common ancestor with positive probability. And if alpha is between 1 half and 1, then two lineages will almost surely coalesce. But the time to coalescence is, the expected time to coalescence is infinite. Okay, that's already something quite disturbing, but there is no avoiding it. It's a property. And if alpha is bigger than 1, then you got some Kingman-like behavior. Okay, I hope I'm using the right notion of alpha here, because sometimes alpha is alpha plus 1, but I think that's correct. No? Backwards in time, then you have some insight of what to expect. Forward in time, and this is the wrong title here, I should have put forward in time. There is also some insight, but we don't have a full stochastic differential equation describing the allele frequency evolution for the regimes where the tail is fat. Okay, and what we are able to say is that when the tail is fat, we can say if y is the ratio of one type in a two-type model, one allele in the active population, we can say that the correlation of this fraction at generation n and the same in generation 0 persists also as n goes to infinity. Okay, whereas you would expect complete, sorry, and it stays between 0 and 1, excluding 1, right? And that means that there will be, in the graph, there will be unconnected components that persist. There will be no common ancestor, so there will be not a unique tree, right? So there will, so the frequency, the correlation with the past will still be alive, let's say, but not in a ultimate way. So you don't fixate essentially, even if you would normally. Okay, and the proof is obtained by some manipulation of renewal theory and Zabirian theorems and some reference that we must have had in our hands, but there was some mystery of what happened to it. And fortunately, Ilgelbring and Wacholbinger recently have reproved some of the true statements that we made, but for which there was some kind of mystery about. Yeah, anyway, ingredient. Okay. Now, yes, the Seedbank coalescent can be seen as a, as fitting these statements about the regimes about the tail of alpha, the Seedbank of Blatt et al. 2016. And the other thing that is interesting to observe is that when the tail is scaling with alpha less than 1/2, then you can say that, for example, there is a connection with the fractional Brownian motion with Earth parameter alpha plus 1/2. You need to, in order to see the connection, you have to imagine a population of size 1. And then there is still a graph with arrows generating a tree. And then by appropriate labeling, you can see that the frequency process is still something non-trivial because the types may keep switching between 0 and 1. You map 0 and 1 to +1 - 1, and you get the fractional Brownian motion as a scaling limit, right? That's also something that has been recently proved by nice martingale arguments by Ilgelbring and Wacholbinger in the same paper. And but apart from that, there is not much known of fat tail Seedbank reproduction, especially forward in time. So for long, we have dreamt with Jochen to generate a fractional version of the Wright-Fisher diffusion. There is some fractionality going on, but yeah, we'd like to see it happen one day. Yes. Yes.
So if you really put mu to be a geometric,
Mm-hmm.
you would have something that does both things.
No, you have infinite time a common ancestor. It doesn't have to be a Kingman. Is that right?
I mean, you can prove that.
Yeah.
My point is that
yes.
to really get the model,
yes.
A geometric of expectation n where you use the population size, which correspond to mu being alpha equal to 1.
That is right. That is right. Yes. Yes. But yes. Yes. But yes. So that all combines. So I mean, the both statements are true. Yes. But I see what you're saying. Yes, I agree. Okay. So one way of introducing fat tail in a tractable way comes from looking a bit closely to a recent paper by Denolander and Homan, and Greven, sorry. And the idea, they like to generalize models, as everybody who have read the paper have realized. So it's a big class of new family of seed banks. And I'm only looking at a particular case where you have one active and infinitely many possible reservoirs to go to sleep to, right? This is a generalization of one model that I think Adrian Jochen and co-authors had in 2018, where you had a finitely many reservoir and one island. And of course, the dynamic is easy to understand still. The diagram is the same, except that you have distinct rates, possibly, to choose the island, the dormant island to go to, okay? So in this case, you have a rate E1, K1 to choose island 1 to go to sleep to, and then you wake up with rate E1 again. And K1 then represents somehow the relative population size. Sometimes this is denoted by 1 on K1. So in case the equations later on doesn't sound right, it's just that because I'm using inverse of other people's parameters, preferred choice, okay? And you do this. So already in Greven et al. Paper, there is this statement that when the number of islands is infinite, you can generate fat-tailed distributions for the waking up time. And so I'm going to talk a little bit about it. So these Km parameters, if you sum them together, describe the relative size of the dormant population or with respect to the size of the active population. And this sum can be infinite. That's not a problem. What you need to guarantee is that if you sum together all the rates of going to sleep, right? So this is the propension of becoming dormant. You want it to be finite. That's a natural assumption, as we know, because otherwise everybody would immediately go to sleep, which is not a bad thing, but not in the model. So if you denote with a parameter sigma the overall go to sleep time for an active individual, and I can see a typo here, there shouldn't be an M here, then you can prove that the probability of distribution of going to sleep is still an exponential with this parameter chi that I denoted before, right? So that makes sense. It's the overall rate of going to sleep. But the wake up time is a linear combination of the time of waking up if you know in which island you are, right? And the mixture appears to be sensibly made by the probability that when you go to sleep, you choose exactly the island M. Okay, that is the key point actually. And Greven et al. Also say, okay, if you choose Km and EM and all the parameters appropriately, you can generate fat-tail distributions. And what I'd like to do is to see what's happening at the level of the forward in time dynamic. Where do you see in the equations the memory, and what happens to the stochastic delay differential equation? Okay, and that's one first description that shouldn't surprise anybody here anymore. So this is the SDE corresponding to the joint distribution of the active island X proportion. We are looking at frequencies of one type over the rest, over the other. Yeah, and in the active island, and YM is the frequency of dormant people in of type 1, say in the dormant island N, right? And M is indexed by the whole set of the integers. You put an initial condition, and that's your SDE, right? So this is really the Seedbank model of Jochen, Adrian, and Al, extended to infinitely many reservoirs. Okay, so if you look at the joint system, it's still a Markov process. It's an infinite dimensional system that jointly is Markov. So the fat tail that we were talking about can be incorporated in an infinite system of Markov, collectively Markovian system. Okay, and therefore you don't see much of sort of beauty in terms of memory. Actually, you do see it, but you need to investigate very much into what is this fat tail is doing in this Markovian system, because Markov systems are memoryless, right? And some insight may come from an SDDE interpretation. And so that's, I think, one of Jochen's hot topics, I think. And so I'm very thrilled by learning about these SDDs, because I haven't coped with them for a long time. And so it is very easy to prove that the solution to that SDE as a SDDE representation that looks like this. So this is the delay. The red component tells you more explicitly about the memory of the process. So now in this representation, you can see some fat-tailed element popping up. And of course, another thing that is nice in this representation, as is already been seen previously, is that this system, this active population, is the only one that experiences noise directly, say. And in this equation, there is no appearance of ym anymore. So the y's come about only through the initial state. And of course, the ym is instead affected by the state of x. And so it's nice formally, let's say. It's talking about the same object. It's still a system that you can see, and it's very useful to see these two sides of the SDE in a way. On one hand, a Markov system, on the other hand, the stochastic delay system. And so now what is, okay, yeah, this is just to convince you that proving it is not hard if you see closely what's going on. You just use what known integration by part formula for continuous semi-martingale, where f in our case is taken to be deterministic, so that's what we can write. And then you take for your continuous semi-martingale ym, and for f you make an appropriate choice. Maybe that's a bit less intuitive, but this is made to simplify the equation in the nicest way possible, and you obtain this. When you obtain this, you just divide by this exponential component, and you get your own individual delay just there, and plug into the system, and that's where this component comes from. Once you divide by ET, and then substitute in X, and you're done. Okay, it's quite neat, I have to say. So I learned something. What I learned also is that the term that incorporates delay is always expressed in this form. And on one hand, it shouldn't be surprising because this is one object that we have seen, similar to what we have seen at the beginning of the talk without copying with SDDEs. But now we see the actual memory and its fat tail, possible fat tail, appear explicitly. And there is a probabilistic interpretation, if you like. So if you consider PM to be the probability that if you fall asleep, you choose, I mean, that you will choose the M island to fall asleep to, then this is, of course, a probability mass function on the numbers, on the integers. And then this is a probabilistic mixture of exponential densities as opposed to exponential survivals. But what is a probabilistic mixture of exponential densities? In general, a probabilistic mixture of exponential probability density functions is something very regular, and it happens to be a completely monotone function. So there is some case to believe that this structure could shed some light, if you look at it formally, into how to deal with stochastic delay differential equations of Seedbanks. So in particular, there could be a case for deriving a further extension of the model where we may extend this discrete mixture of exponential to a continuous mixture of exponentials, right? So, and the intuition that is triggered by this infinitely many islands model is that the thing that you need to do is perhaps to have a continuum of reservoirs and not only a discrete set of reservoirs, but everything should carry through. Okay, so let me see what else is in this slide before I forget. Well, one thing I want to say is that this mixture of densities can also be interpreted as minus the derivative of the survival function of the wake-up time. And that's exactly the connection, right? So this minus the derivatives is really the cumulative distribution function of the wake-up time, you know, derivative of the cumulative distribution function. So this is the density of the wake-up time. Yeah, so everything is, you know, holding together. So what happens is you got that the delay, the memory function that appears in the delay equation is really the density of the wake-up time. What would you expect? I mean, I would expect that, but now we see it clearly, okay? And then the other bit of information is that we have a structure that is for phi that tells me that you got nice regularity properties encapsulated in the notion of complete monotonicity. For example, you got that all the derivatives exist, and if you take -1 to the k times the k derivative, you always get a positive object. Okay, and so that may get us lucky with calculus. Okay, so this is my extension that is very invisible, but that's what I was talking about before. So the idea is just to have a continuum of islands, and you have a rate that now is a function of this set of islands. You can imagine this is as a torus or whatever you like. It doesn't have to be. Why do I like to put it as a circle? That's actually important. The dynamic of this mimics what happens in the multi-island model, but it is important to realize that it could be also a limitation. What happens is that if you go to sleep to island M, before visiting another island or reservoir, you need to wake up first, right? I insist that this is not necessary in biology. And actually, I saw talks where you were saying that, you know, you can move in space and remain dormant. But it's very easy to believe that if when you sleep and in the meantime you move in space, also your propensity to wake up change, right? So that means that you are really moving to another place there without being awake, right? So this is something that I'm exploring. I would say at the moment, but I remember that in 2019, in the previous workshop, I was saying that was work in progress. That's what I'm saying, that my there is some latency going on in my memory research. Okay, so anyway, so that's an important feature of all these moments. And I mean, it's easy to conceive how you can generalize all the conditions that I stated before in the discrete setting, right? You just need to choose your own favorite densities, and you have to make sure that you don't go to sleep infinitely fast, and so on, right? Everything carries through almost painlessly. And this is my claim. I would say our claim, but because this could collapse because the devil is in the details and we didn't look at the devil yet, it's just a proposition 1 plus epsilon, right? So when epsilon will be 1, we will be done. So, but that's really our very well educated guess. So this would be the SDE of a continuum island model, right? There is a bit of nervousness because now the parameter R is continuous. So is this an SPDE or not? My claim is it's not worth looking at it as an SPDE because you wake up every time you need to visit R plus epsilon, but that may be a stretch. In any case, I think that this would solve the SPDE business. There would be a dominating density that you can make differentiable and so on. So, but structurally, this is what I would expect to see. And here you would have a complete monotone function. So now the gist is, you want to give me, I mean, we can look at it the other way around, right? So if you give me a completely monotone function, I can give you perhaps a Seedbank model straight away, right? So that's a characterization of possibly a complete characterization of these things, right? So we may argue that. Actually, it would be nice to shed more light in which types of completely monotone functions we need. I mean, maybe it's not the full set of completely monotone functions that are compatible with this setting. In particular, we need some finite expectation going on here. I mean, we need this condition that may limit the sort of size of the tail or some other feature of the mixing measures. But it's nothing too painful. So surely you can get heavy tail distributions, definitely. And I think I have an example here. Yes. So if you take phi of t of this form, and remember, well, this is quite well in the same form as Greven and Alt's suggestion. What you get is that if you plug it in the SDDE, so if your memory function of the Seedbank scales like this, then your delay component in the SDDE becomes a fractional integral straight away. And that will make things hopefully more computable because there is huge literature on fractional calculus and so on. So, and this is how the system of equations would look like, okay? So by the way, this is already in the continuum of island setting, but this is not depending on how many islands I'm choosing. So they have to be infinite in order to have something like that. But apart from that, they could be a discrete setting of infinite countable set of islands, okay? So surely, proposition one, surely this already applies, okay? So if we recapture the suggested parameterizations of Greven et al., we have a system that can be addressed computationally or whatever with tools of fractional calculus. Equally, if we view this from the point of view of SDDEs, which is this, so there would be a fractional derivative, there would be a fractional derivative. But, apart from the noise, the suggestion is also that we could have a way of getting an interpretation of generic sort of fractional Volterra style integral differential equations, right? When we see something like this in other contexts of mathematics, we could disentangle that and think about it as a kind of potential Markov process where all the Markovianity can be unfolded by inspection of the completely monotone function that is in there. So that's also something that I find fascinating. One remark I want to make, I think I don't know how much time I spent because this is still the first slide of the talk. No, just kidding. But how much time do I have? Then 20. That's a lot. No. I'm happy with. Okay. No. Okay. I thought I used already my full hour, but yeah, no. Then I'm doing well. And now I forgot what I wanted to say, but yeah, it will come back. Yeah. Yes, I remember. Thank you, because I saw you. I remember. Yeah. No. Please go ahead. No. You should because. Yes.
Can you obtain directly from the discrete model of Greven? So, like in scaling somehow the space in order to work with the continuum.
No, you can have, no, you don't have to have a continuum of islands if that's the question. So you can have, I mean, it's sufficient to have an infinite set of islands. Okay. And the other thing that is a specificity is that you have to transition from a dormant always to the active one, and then perhaps move to another one. Dormant.
From the, let's say, model of Greven, etc., you obtain this fractional because like there are these traits that
right. So I think that possibly I did a detour in the continuum of islands, and when I saw the SDDE, I said, "Oh, that sounds like an integral, blah blah blah," and that was not super, immediately clear to me. Knowing that, Greven has said, "Okay, this is a fat tail," and also it is possible to look at the SDE, right? And then if you plug in generically, you have to make the observation that this can be a metagrapher, essentially. And you can get it also from, can be approximated by a meta. Oh, that's, okay, maybe you do need a continuum of islands. You're right. So, yeah. You're right. Okay, so let me rephrase my claim. Oh, thanks. Greven said that this should scale like a metagrapher. Yeah. And in my brain, I was already replacing with a metagrapher. Yeah. But to have the metagrapher, you do need a continuum of islands. That's a very good point. Yes. So this is yeah, good. So you don't. Yeah, absolutely. So this is okay. You can use fractional calculus to approximate this. There is a kind of a yeah, well spotted. Good. I bet you do. That's why I remember what I wanted to say. Yeah, the other thing I wanted to say is that, look, I mean, that's nice and sweet. Actually, I'm very happy to have all these properties. Where am I? Yes. Look, the fractional component, however, doesn't affect the noise. Okay, so we don't have a fractional Wright-Fisher diffusion in the way I wanted it. I don't know who cares apart from me, but the thing is, my first conjecture ideally would be maybe heavy memory would give me a Wright-Fisher SDE, except that instead of the Brownian motion, you would have the fractional Brownian motion. That's not happening here, but I would argue that, if you don't care about biology and you care about mathematics for a moment or for your life, there must be some insight onto what you need to do in order to get fractionality also in the noise. Maybe you don't need a population genetic model, but it would be nice to have an individual-based model that will generate that. We don't have that yet, but again, look, we are looking only at a transitional dynamic that works like this. So there could be other ways of getting where we want. And independently of the quest for the fractional Wright-Fisher, it makes sense in biology to also look at other patterns. Okay. And I have a last slide after my talk that will be too long, and I put it in the appendix because I know that I will not have time to talk about, but where there is a proposal of a potential extension of this, or no, there's a deviation from this, essentially. Okay. Let me see if I said what did I want to say. Yeah, so there is this specificity because of this connection mechanism between one center, which is the active, and the sort of circumference, which is the island. Because of this diagrammatic setup, the times to go to sleep are always exponential. Yeah, the time to return to active, if you know where you are still exponential. That's why the joint Markov is system, joint Markov SDE is Markov. So what is responsible for the fat tail is that the memory, when somebody exits the active population, integrates out the information about the choice of island that this particle has made. Is that clear enough? Okay. Yeah, so, okay, is it practical? So now that we have a nice representation, what can we make of it? In particular, in statistics, now that you have a description of how the allele frequencies evolve, you would like to make them tractable. You may have, for example, observations from a trajectory of allele frequencies, but only partially collected at distinct time points. Or you could have, for example, a continuous stretch where you are able to observe the full frequency, right? So maybe in a lab, you can approximate your lab experiment as an observed piece of trajectory, and you'd like to make inference about the parameters of the process based on that. So one ingredient that is important, or would be important, is to be able to simulate to sample trajectories from the model. And so you'd like to have a analytically explicit solution of the SDD, which obviously is never going to happen, or maybe it does, but you know, it's a very big deal. So you don't have to have dormancy to complicate this enterprise. Even with a simple two islands model, you don't have a full analytic explicit transition function available, right? So you need something else. For example, an exact simulation technique. You may not be able to write down a closed formula for the transition function, but you may have an exact simulation technique. And also, this is a big deal, even not thinking about dormancy. Okay, even when populations are fully active, apart from a few cases, actually a conspicuous class of cases, you know, there are especially migration models with migrations, for example, are not entirely simulable exactly. And so if that fails, we resort to an approximation technique. And now this part of the talk is summarizing something that I've started recently to have conversation about with Massi Tamburrino, who is a colleague in Warwick, and who has done something about general SDEs that is kind of suggestive, and so we're trying to exploit that a bit. So what has he done? So the following, billion slides are shamelessly copied by slides that he prepared, but with much nicer graphics. But that's the setup. You are concerned with this SDE, where X may be a vector, or actually even a matrix, but let's say a vector. And you got this shape for your SDE, and that's your noise. And the noise is, is additive. And you would have a Wright-Fisher term here in our case, but it don't work with this type of equation, okay? And the assumption is that this drift can be decomposed in two components, and this N has to satisfy certain regularity properties, right? This is a list. I'm not going to spend too much time on that. And crucially, the matrix here appearing in the noise may lead to hypoelipticity, which means it could have a zero component. That's actually what happens in the Seedbank, right? So in the Seedbank, you got that the noise affects the active directly and the dormant only indirectly through the active. Okay, so that is the hypoelipticity possibility. So that's what I like about this setup. What I don't like is that there is no Wright-Fisher term here, so we have to cope with it. Okay, so we need these two components to be friendly enough. That's all. Okay, and the objective is to come up with a discretization, a numerical method to carry out sensible, approximate sampling for the process. And the typical prescription is you split the time into equally spaced mesh of intervals. And you will construct on this discretized time setting a numerical solution that approximates the true solution at those times. And the you know, Euler-Maruyama scheme is the most famous technique for this, and it's one example. Okay, so what are the characteristics that Massey wanted to preserve? And that's what Euler-Maruyama don't guarantee in the hypoelliptic case. So we would like to preserve these things at the same moment, you know, simultaneously. We would want not to give up any of them. So we would like a nice R mean square convergence property like this. And also, we'd like to preserve the properties of hypoellipticity. What does it mean? It means that if the original SDE is hypoelliptic, also the one-step transition from the approximating process value at state 1 is maintained when you transition to state 2, right? So it's immediately reflected into one step. And also you want to preserve also ergodicity properties. For example, if the original process is geometrically ergodic, you want this to be reflected in the sampling scheme. And also some sample features. For example, in our case, we are looking at frequencies. If our approximating method exit the 0-1 interval, maybe we don't like that very much. And yes. Okay, 5 more minutes. Okay, well, the thing. Okay, good. So this is the program that Massey has set up for his own stuff for that SDE. So essentially, you identify a clever way to split the equation into sub-equations that are individually explicitly solvable. Then you solve them. Then you compose the two solutions in a way that generates a good approximation. Okay, that's all. And I skip the details of what Massey has done for this particular SDE, but I want to, well, the main bit is that from the A component and the noise, it could recover the first exactly solvable solution, and from this N component, the other bit. Okay. Now, let's for a moment think about this being a Wright-Fisher noise and not the additive noise, say. Okay. Even if we took this bit, this component here, to be the usual Wright-Fisher drift term induced by, say, mutation and selection, we would not have an explicit solution to it. But we would have an explicit solution to this part in the SDE of an island model. Okay, so this would be the delayed part in our case. And this would be a Wright-Fisher setting. But this Wright-Fisher setting doesn't have an explicit solution apart from a few known cases. And the good thing is that there is anyway a way of simulating exactly from this solution. And that saves the day. So now, if I run out of time, I said exactly the bulk of what I wanted to say. So that means that it is possible to extend this method if you are prepared not to have an analytic solution of that, because this solution can be carried out quite for free. Okay, everything else is formula. Okay, blah, blah, blah. And there are several ways of compounding the two solutions, but this is not my domain. So even if you ask me about Lee Trotter, I would have to make a phone call to Massey. And that's all. I think I covered the bulk of the material. I'm very happy that you've been listening until now, and I'm open for questions. Thank you very much.